So in this case, we have our two vectors, and they're both position vectors. And we want to add them together. So this would be like if I gave someone instructions, I want you to move 101 millimeters to the right, and then I want you to move 183 millimeters, 55 degrees from the horizontal. I want to give them a single instruction of how to move that's going to get them to the same place. So what we always need first, some coordinate system that's convenient. In this case, I'll say x is right, y is up. Again, for convenience, they are orthogonal to each other. They would not have to be an orthogonal system, but for it to be Cartesian, that's how it works, is that they're always orthogonal. So I'm going to say x is right, y is up. I'm going to take these two instructions, I'm going to draw them emanating from the same origin. It's just going to be easier this way to do it that. So I have these two vectors, or these two sets of instructions. I want to find the resultant. I want to add them together and find the resultant that I'm going to call R. So find R, and the resultant is going to be a vector. So what I cannot do, it would be nice if I could, but I can't say, oh, the resultant, I can just add these together. That's 101 plus 183, that's 284. That's at 0 degrees, that's at 55 degrees. 0 plus 55 is 55. And say, that's my answer. The resultant is 284, angle 55. Polar does not work this way, unfortunately. And that's why we use Cartesian, because we can add the like parts of Cartesian coordinates. So that will not be our answer. But if we express them in Cartesian coordinates, then we can do that. So first we have to decompose our vector, or express each of these in their ij component form. So we want to know how much of each vector lies along the x and how much lies along the y. So we'll start with an easy one. How much of the 101 millimeter vector lies in the x direction? Right, all of it. It's parallel to my x direction, so 100% of it lies along x. So in component form, I can write this as 101i plus 0j. And I'll call this vector P1 and P2. So this is how I can write vector P1, 101i plus 0j. So that was convenient because it was parallel to, I made x to the right because it was convenient, and it turned out that helped. But if I look at vector P2, it's a little bit different because it doesn't lie only in the x or only in the y. It lies a little bit is in each of these directions. So for vector P2, I want to find how much is in the x, how much is in the y. What I can do is I can create a right triangle where I can have a component in the x and a component in the y. We see here, these are, again, two equivalent instructions. Start here and end here, either by going along the hypotenuse of the triangle I just created, or start here, go to the right, and then turn up, and I end up at that same place. So what I want to find are, this leg is the amount of the vector that's only in the x direction, and this leg is how much of it is only in the y direction. So these components are going to make up the I and the j components of my vector. So for the I component, what is the length of this piece of my vector? Because I made a right triangle, and I can do that because it's a Cartesian coordinate system, I know this leg is the hypotenuse times the cosine of 55. And then that's I hat, because that's how much of it lies only in the x direction. So what component of it is parallel to the x? That's the number I write up here. And I can get this as a decimal. This is going to be 105 in the I hat direction. Now I look at the vertical leg. This is how the coefficient in front of the j. So how much of it is in the j direction?
183 centimeters.
Yeah, so it's just in this, with respect to the 55 degrees I was given, it's the opposite leg. And that is going to be 150 j. So if I've expressed P1 in ij components, P2 in ij components, I now can say, if I add these two things together, I get my resultant vector, which is r. In Cartesian coordinates, now it's as easy as adding my like terms. I add the two I terms together, so that's 206I. And I add the two j terms together. 0 and 150 is 150. And in Cartesian component form, that is my vector. It has components in I and j. It's a vector quantity. And if I were to draw this, not to scale, but I have to go 206 to the right, I have to go 150 in the j, and then that's where I'm ending. Or I can just go along some diagonal line and end up at that same point, if I know how far to go and at what angle from the x-axis to travel. This is the Cartesian component form of my resultant vector. They are asking for the polar form. So I know this information. I now want to go in the opposite direction. I want to find the direction and the magnitude and report that as my actual final result. So what I want to first find is what is the magnitude of vector r. This is how I can represent magnitude, is the vector inside two vertical lines, or if I just write r without the line over it, this is a scalar quantity, and that indicates it's not the vector r, but it's the magnitude of that vector r. So how do I find the magnitude of vector r? Right, it's a right triangle by design. I can use Pythagorean theorem to find this magnitude. In this case, I know the legs. I want to find the hypotenuse. So it's going to be the square root of 206 squared plus 150 squared. So the magnitude of this vector r, I get 255 millimeters. Actually, I made a slight error here. This does need the units attached to it for it to be correct. So magnitude is 255. And now I want to know what's the heading. And this is x and this is y. To find the direction, we always use the counterclockwise angle as measured from the positive x-axis. So this is the angle that we're looking for here. I'll call it theta. Right, so how can we calculate theta?
Tan inverse 150 by 2.
Right, again, we have this right triangle by design. We can take the 150 over the 206. This is in quadrant 1, which will not always be the case, but here we're in quadrant 1. We get that the angle that makes with the positive x-axis is 36.1 degrees. So an alternate way to write, we already found r bar, or the vector r, in Cartesian component form. Alternatively, we can write it in polar form. It's equivalent, just expressed differently, as 255 angle 36.1 millimeters. So same vector expressed in polar, expressed in Cartesian coordinates. Specifically, though, this question was asking for the polar answer, so this is the answer we would want to report.